We're in your chemistry, chapter 8, the periodic table, how to classify elements. So here we have a picture of Mendeleev's periodic table, one of the first, of course, he put together that periodic table. And of course, you can see it's all in Russian there. So you can see how important it is now that we have these tables and how to classify these elements, because some have very similar characteristics, and that's what we're going to talk about, how our periodic table can tell us about other elements. So where did we get them? Where did he get these ideas? Well, it says from ancient times just until 1669, there were only about a dozen elements. And then between 1737 and 1869, we had 49 new elements. And chemists noticed that some of these elements had very similar properties and started grouping them. The first to group them were, the first guy was actually a German, and his name was Dobereiner. And he put together, Johann Dobereiner put together these triads. He called them triads. And these elements were groups of 3 triads that had similar properties. And it's very interesting, too, that they had atomic mass was the average. The middle one would have the atomic mass as average. So let me show you this picture, see if you can see here. At the bottom, do you see? Here was some of Dobereiner's triads. And you can see he had sulfur, selenium, tellurium, and as you can see, the middle number was an average between the other 2 numbers, chlorine, bromine, iodine, the middle number. And here we have calcium, strontium, barium, the middle number. So he grouped them in groups of 3, platinum, iridium, osmium, and he said, wow, something is going on here with the atomic masses, as he looked into the way they were classified. Now this was in, the year was 1829 that Dobereiner did this. Now, the next, it was later on in 1864, so, at least 30 years later, over 30 years later, a man named John Newlands from English, he was English, proposed a different system of classification than that. What he arranged the elements in order as increasing in their atomic masses, he noticed there was a repetition of properties at every 8th element. So he thought it looked like octaves. We'll call them the law of octaves. Octave meaning 8. And so he put them in groups of 8 now, and he called on that arrangement, and he thought, this is kind of like music in octaves. And so he put it together, and it looked pretty nice, at that point. But still, we had new elements coming, and not until Mendeleev, which Mendeleev was in the year 1871, which was, not even 10 years later, he put together a whole periodic table. And that's what we're going to be talking about in this whole chapter. So Mendeleev's periodic table, in 1860s, actually there were 2 chemists, Dmitri Mendeleev was one of them, and he based his periodic table on chemical properties and published it in 1871. But Lothar Meyer was a German, and he made a table too on physical properties. But Dmitri's Mendeleev's was quite a deal. It was, very, very in depth that as he put it together. And we'll show you that in just a little. But it was based on these chemical properties. And Mendeleev's now is very similar to the periodic table that we have today. So here's a picture of the periodic table here, kind of background there. You can see I have one here, periodic table. So you can't hardly see there. I'll put it up later on when we don't have the background. But anyway, the periodic table. The periodic law. First, Mendeleev said the periodic law. Here's the statement of the periodic law. And you probably have to know this. And this is the idea that the properties of elements are periodic functions of their atomic mass. Okay, what's an atomic mass? Do you remember? Atomic mass being that mass that has the nucleus, mainly in the nucleus and the electrons. It's actually the mass of the whole atom, but it contains neutrons and protons both, right? So that mass is going to be different than the atomic number. So we put together it on the atomic mass. When Mendeleev put these together, he also found that there were some other as he put them together, he saw that there were some other blank spaces, I should say. And in these blank spaces, he left them blank, but he could predict the element that would be between those two elements just on the characteristics. And so he even named some of these elements that hadn't been discovered yet. So he named one element AK aluminum and one AK silicon. And AK comes from Sanskrit meaning first. So AK silicon may be taken to mean first comes silicon, then comes aluminum. So he actually labeled these elements before they even were discovered, because he knew there was a blank place in between, that there must be an element to fit there. So he named this element and even described the element that would go in that position. So it was pretty amazing to be able to do that on his table. And he predicted the properties of other unknown elements too, and they came just as he predicted. So in fact, two of them, germanium is one of them, and gallium, he predicted before they were even discovered. And he put them in his table. So, and it turned out all to be just like he said they would be. So it was almost like he was predicting the future, but he did, because there was a blank place in his table that he knew that there needed to be another element with atomic mass, or now we know it's atomic number, but that atomic mass there. So he knew there had to be, but he didn't know what it was yet. And surely it was. So, and here we have the predicted and actual properties of gallium and germanium, those two. Eka aluminum and eka silicon, he said first. But here we go. He found that the atomic mass actually was 69, in the 69.7, 72, 72, and the actual, he predicted it was 69, and it was 69.7. He predicted it was 72, and it was 72.6. He was not too far off. And he even predicted the melting point and the boiling points, what temperatures they would be, and they were very close to those temperatures as the characteristics. And he put together the formula of oxides with them. So he said, basically knew how they would combine with oxygen even. And the densities, he knew all these just because they were predicted between two other elements on the table. So that was pretty unique. So going on here, there was another guy, and his name was Moseley. Let's go back here. I think he was in the bottom here. This other, here he is right here. Henry Moseley. Well, Henry Moseley in 1913, he took Mendeleev's, because there were some mistakes. They couldn't figure out some of the elements, wouldn't fit. They placed iodine in a column of bromine. They said, and Mendeleev said, they must have the atomic weight wrong or something, because they didn't fit in right. And so he couldn't get them. He said, there's some measuring the atomic weight wrong, or something is wrong. And so there was some discrepancies with Mendeleev in some of his elements. And so in 1913, Henry Moseley showed the different wavelengths of X-rays on the X-ray spectra to the elements. We're talking about clear in 1913. Because remember, Mendeleev was back in 1860s, we're talking. And now we have, basically, now we have 1913. Henry is looking at these. Henry Moseley's looking at these. And looking at these spectra, like as you pass through, the elements have certain spectras. And so he was related to these positive charges in the nucleus. And so he said, my goodness, this table is done on an atomic mass, Remember, atomic mass is the protons and neutrons and electrons, all the mass of the atom. But he said, really, they go by the atomic number, which is protons. And actually, the number of protons equals the number of electrons. So the characteristics really were related to the number of electrons, which were the atomic number. And so this explains the behavior of a lot of different elements that weren't behaving just right, and as anomalous. So they basically said, now it all fits into place. We're going to go and put together the periodic table, and on physical and chemical properties and everything are going to be the functions of not their atomic mass, but their atomic number, which atomic number would say the number of protons, which would equal the same. There's the same number of protons and the same number of electrons, so it would equal the electrons. And so this would have to do a lot about electrons, as electrons have a lot to do about chemical reactions, don't they? That's what we're finding. Now let's go to the last part here, and this tells about the atomic number and how they saw how the atomic number was related. Here's the molar volume and the atomic number, and you can see the property goes through repeated cycles of peaks and valleys. And these elements of the peak were telling us basically that we needed to go by as the atomic number went up, there were peaks, and these were similar. Helium, potassium, rubidium, cesium, these were all going to be in the same category. These here would be in the same category here as we went through, and these fit in the same categories, and you saw, and it was all because of their atomic number. So that's pretty amazing, isn't it? Let's look over your section review really quick, because these will probably be pretty easy questions here, since I've already went over them. Tell the contribution of each of the following development of the periodic table. Dobereiner, remember, he put together those triads, elements that look together like threes with their atomic masses. Newlands, as we said, Newlands put together the octaves in eights, right? And then Mendeleev put together a periodic table, but the periodic table was based on atomic mass, which means the neutrons, protons, and electrons all together, the atomic mass. And later we find Moseley, he said, it's not atomic mass, it's atomic number. It's the number of protons or electrons. And that's what we have today in the periodic table of today, the physical. And on to number 2, suggest some reasons why Mendeleev's periodic table was accepted by scientists. It was accepted by scientists because they did see that Mendeleev, he had them in groups, and he even predicted these groups, predicted elements that were in these groups or between atomic numbers, and predicted them so accurately on. They said Mendeleev's periodic table must be accurate. He has something going here, this Russian. So on to state the modern periodic law. The modern periodic law, the law that we have today, the periodic table. What is the periodic table? It shows the physical and chemical properties of elements are periodic functions of their atomic numbers, not atomic masses, atomic numbers. So that's go on. So let's go on to section 8 here, 8.2. I'm going to show you here this whole classification. This is our periodic table. So now we have classifications, and you're going to see here, certain classifications: metals, semi-metals, and non-metals. And so this is what we're going to talk about. How do we classify these? Because you can classify an element not only in a metal, a semi-metal, and non-metal, but also if they're in a certain group, they'll have certain characteristics. So let's talk about the classification system here. So elements in the same column are going to be in the same group. So these are groups. So each column will be the group. And then elements in the periodic table, some of the elements will be in the same row, and these are rows, okay, just so you know. And there's going to be all these different rows. There's 18 rows, or 18 rows here. 1, 2, 3, 4. It's labeled all the way across here over to 18. It used to be the Roman numerals, but now they put them in Arabic numerals. So that's how they're put together. They're the same. These are in the same group. And then, of course, we have all these different groups located next to each other in these assigned numbers. And these rows of elements are called periods. So if there's a row of element, all these, this is this period. This would be this period, the second period, or this period, this period. So you can tell which period they're in by the rows, and then the groups are down. So at first, we looked, and there were some general classifications of these, and some of them, of course, were metals, like I said, and some were semi-metals, and they had both characteristics, and some were non-metals. The yellow ones here are non-metals. The blue ones, all these blue ones here are metals, right? Let me put this up so you can see the bottom too. There we go. So the characteristics of metals, what do you call a metal? A metal will be called because of its hardness and its stiffness, and it's a good conductor of heat and electricity. That's a metal. That would be all of these metals. A non-metal would be very brittle. It wouldn't be hard, it'd be very brittle. And it also, some of them are gases, and they'd be non-conductors, insulators. They're very dull, they don't conduct electricity very well, and they don't conduct heat very well. So they'd be more of insulators. They have a dull surface. And then there's the semi-metals right here, this whole class of semi-metals, and they are also pretty dull, although they conduct heat and electricity better than non-metals here, and you'll find that some of these are very specific. We use a lot of these semiconductors, especially silicon. We use the silicon here as a good semiconductor for computer chips, of all things, So semiconductors are used for a lot of things, transistors and computer chips in this area. So those are semiconductors. So we have those in non-metals, semiconductors, or semi-metals, I should say, and metals. So semiconductors are semi-metals, the same thing. So, and another way to classify these would be the main groups. And so the main groups represent the elements, certain elements in these columns. Main groups would be column 1, this column 2, this column 13, this column, 14, 15, 16, 17, and 18. So basically these two columns, see how they're up here higher? And all of these would be the main groups. So if you're in any of these columns here and over here, starts up here, the ones that are elevated here, they would be the main groups. And the main groups are a lot of representative main group elements, represent elements of the different, not only different metals, but also a good representative of these different. The first row here, okay, well, let me let's go back to that, the main group. We have the main group, those are the main groups. What's the other group? These middle ones here, they're all called transitional metals. So we have this, these are the main group elements, and these are the transition metals. So main groups and transition. And then we have the inner transition metals, and these are the two rows that are below, right here. And the first row is the rare earth. They call them the rare earth. And the second row, would be that's basically called our radioactive elements. So let's go over that too, because you're going to have to classify these. Remember, we have the non-metals, the metals, and the semi-metals. Okay, we did that. Now we have the main group, which are 1, 2 in these groups, main group. And then we have the transition group, they're transitioning. And then we have the inner I call them inner transition down here in the bottom. Okay, so now let's just talk about these main groups. What are the main groups? And so we have group 1 here. Group 1 are called the alkali metals. Alkali metals here. And they have, lithium, potassium, sodium, potassium, rubium, cesium, all the way down here. These are your alkali metals. And they used to call the alkali metals because they thought them as they represented like ashes of plants, which we know they don't, but that's what they thought in the beginning. So they called them alkali. And these are found naturally only as ions. That you can't just find some sodium without sodium being an ion, being charged particles. So they're usually found as ions. They're never found as free elements. So that's group 1 metals. Group 2 metals, this group here is basically your alkaline earth metals. And these metals here are similar to the alkaline, but they don't react as easily as do the alkali, right? And these were originally found in the earth, not in the ashes. So they called them earth, alkaline earth. So these are alkali metals and alkaline earth, those two. Then on to over here, 13, 14, 15. They don't have any special names really, but they represent these columns, 13, 14, and 15. And they have some non-metals and semi-metals and metals in there, so they're a mixture, 13, 14, and 15. And on to group 16, a very important group because it has oxygen. A lot of these have characteristics the same as oxygen. They call these chalcogens. Chalcogens, the oxygen family, right here, 16, oxygen family. And then, of course, 17, we have what's called the halogens. And halogens, that means Greek for salt, because they form salt when they combine. And so the compounds are naturally with ions too. So they actually combine a lot with these over here, easily combining. So these are called halogens. And then the last group is a very important group here. This group, group 18, those are the noble gases. And they used to call inert gases because they don't really react. They thought they couldn't react at all, but now they found out they can, so they called them noble gases because their valences are full. They don't combine easily with other, other elements there. So they're called the noble gases. So those are the categories. So remember, we have the metals, semi-metals, non-metals. Then we have these columns. We have we have the main ones, the main groups here, and then we have the transitionary groups, and then we have the inner transitionary groups, and then of course I went over each one of those columns. So let's go to the next section. So you can see here some of the things. Here is again the main group. Purple is the main group. If you looked in there, remember those 1, 2, and then 1, 2, and on to the main groups of 13, 14, 15. So all these from 13 to 18, and these being the transitional metals, and these being the inner transition. This is the picture of that. And so here we have transition metals. These are all these in the yellow. Some of these are very important transition metals, things like iron, right, and copper and titanium. So these metals are really important in these transition metals here. So here again is the classification of the main group elements. We have the classification of each column here, the main columns here. And as we went for, the first one was the alkali right here, this column. And this column here would be the alkaline earth metals here. And on to 16 would be the oxygen or chalcogens, and on to the halogens, and on to the noble gases. So alkaline metals are green, alkaline earth metals, purple, chalcogens, blue, halogens, number 17, and on to 18, which would be the noble gases. That's how we classify those. So let's go on to the example here. Classify each of the following elements as metal, non-metal, or semi-metal, and as main group, transitional, or intertransitional. If it's a main group element, give the group name if there is one. So let's look at chlorine. So chlorine. So where's chlorine? So let's go back to the, we'll go up here. So where's chlorine? Chlorine is right here, Cl, okay, and number 17. So if we looked back, what would it be? Well, for one thing, we know, is it a non-metal or is it a metal? You know, so let's look back on the next page, and it should tell us. Okay. So we have alkali metals, alkaline earth metals. We have transitional, intertransition, halogens, noble gases. That's kind of that picture there from the table. And there's another picture of that. But let's go back to where beginning we have. We're going to fix it there. Look at this right here is what we need. So if we have chlorine, here's chlorine. So chlorine, of course, is going to be a non-metal. It's going to be in what group? It's going to be in group 17, which is this group, and this group is going to be our main group, so it's going to be one of the main groups. And every element in this column is called a halogen, so it's going to be a halogen. So it's going to be non-metal, group 17, main group, halogen. Then on to uranium. Let's see, uranium. And let's find out where uranium is. I should put it together. Let's see, I have sometimes a hard time finding things on here. Let's see. I can find uranium. It's a metal for sure, and it's let's see. Where it is down here. That's because it's actually a metal here, and it's in the actride series or the intertransitional metals. These are called intertransitional metals. So it's an intertransitional metal, and it is a metal, and it also is in the actride, which is the uranium is the radioactive. I should have known that uranium is radioactive, isn't it? Okay, we have argon right here. Argon is a non-metal, and it's in the main group, because of course this is the main group and this is the main group. It's in the main group, and argon is one of the noble gases. It's in column 18 as noble gases. So let's see, we have iron here. Iron is a metal because it's blue right here. It's blue. It also is a transitional metal because it's in the transitional period right here. These are transitional metals, so that's what iron is. So on to calcium. So let's see. It's a metal. There it is right there. Calcium. Calcium is a metal, and it's in the main group because it's 1, 2, these are the main group. Calcium is a metal in the main group, and it's also in the alkaline earth metals, this one. So it's an alkaline earth metal. It's a metal because it's blue, and then also it's in the main group. On to tellurium is a semi-metal, and it's in the main group. Let's find tellurium right here. So it's in the main group because this is the main group and all this is the main group. So it's in the main group, and it also is is a semi. These are semi-metals. They call them semiconductors or semi-metals. And so it's in that group. And it is also, if you look in this column, it's in the oxygen family, which is the chalcogen family right there. Chalcogen family, which is the oxygen family. So that's it for those two areas. And so you are going to be able to do your quizzes up to this point, and then we'll go on to 8.3.